Looking at acceleration with graphing is also very important. And as we track motion and understand motion of different objects, it's important to be able to interpret the graphs to be able to come to conclusions about data. Okay, so now let's take a look at this situation with the graph. So if we have a velocity time graph, this is telling us how fast. So if we, said 1 second, 2 seconds, 3 seconds, and so on, this could be like 10 meters per second, 20 meters per second. This is telling us how fast. And so this could be like a car going at a constant velocity, 20 meters per second, right? Now in this case, if we had a velocity time graph like that, what's the velocity here? It's 0 meters per second, right? So this is an object that's not moving. So if we look at this one now, over a period of time, 1 second, 2 seconds, 3 seconds, the velocity is getting faster and faster and faster. So in this case, the velocity is increasing. It's getting faster, therefore it's accelerating. So what physical feature of the graph would actually give us acceleration? Again, it's going to be the slope. Our rise now, though, is velocity, and our run is time. So slope equals rise over run. And our rise is velocity, our run is time, and we can get the acceleration, how much faster it's getting. So let's go ahead and try the sample problem. What's the acceleration during part A? So if this was a car, we could see here that it's starting from rest. The velocity is starting from rest, but it's getting faster and faster and faster over time. So if we get the slope, which is the rise over the run, our rise here would be 40 and our run would be 20. Therefore, our acceleration would be positive 2 meters per second squared. During part B, we can ask what is the acceleration. So if we look at part B, we can look at the graph here. If you notice, the velocity stays at 40. So it doesn't mean that it's not moving, but it means that the velocity stays at 40. Therefore, with acceleration being the change in velocity over time, there's no velocity change. Acceleration is 0. Now for part C, what is the acceleration? If we look at the graph here, this kind of skewed a little bit when I got this, we can look at this. We can see that this is a steeper slope, right? So the run here is only 10, the rise is 40, and we can get the acceleration from this. And if we do that, we get an acceleration of positive 4 meters per second squared. So every second it's getting 4 meters per second faster. Okay, so I want you to go ahead and try this one and determine the acceleration from this graph. And again here, this is 2.0 seconds, 4.0 seconds, 6.0 seconds. So I just did this portion of the graph. You could have used the entire graph. So in this case, the rise is 30, the run is 3 seconds. So we get a acceleration of 10 meters per second squared. And we could have used the entire graph. We could have done the entire rise here. The entire rise would have been 50, the entire run would have been 5 seconds, and we would have gotten 10 meters per second as well. So if we were to describe the motion of this particle, it's a little bit strange. If we look at it, the velocity is starting at negative 20. So that means that if this was a car or whatever it was going this way at 20 meters per second. And then after a second, it was going negative 10. So, and then 0 after 2 seconds. So it was going this way, and then it came to a stop, and then after another second, it's going positive 10. So it starts coming back to the right, and it gets faster and faster and faster to the right, as you can see here, 20 and then 30. Something else that is important to take a look at is we can actually find out how far the car goes, the displacement of the car, using this graph. And so if we take a look at an equation that we know, velocity equals delta x over t, and we cross multiply velocity times time, we know that if we do that, we can get the displacement. So it turns out if we had, let's say, a graph like this, we have velocity is 4 meters per second, and we had 3 seconds. If it's constant velocity at 4 meters per second over that 3 seconds, we can get the area, and that turns out to be 12 meters. And so if we're multiplying two, and this is a really, really important idea, if we multiply two values together, we have one on the y-axis, one on the x, we can actually get the that value. And so in this case here, if we wanted to know, okay, how far was the displacement after, was it the origin, or not at the origin, but actually at, starting from rest here, we could get this area, and during this portion of that motion, the motion would be, or the displacement would be 45 meters. Okay, and so now we're going to take a look at position and time graphs. And so with the first one, we can notice here the position over time is constant, right? So every second, the displacement is constant. 1 second, 2 seconds, 3 seconds, let's say 1 meter, 2 meters, 3 meters. So after the first second, it's going 1 meter. After the second second, 2 meters. After the third second, 3 meters, and so on. But here it's different. If we look at the time, 1 second, 2 seconds, 3 seconds, the displacement is not uniform. After 1 second, it hasn't moved very far. After 2 seconds, maybe it's moved to a meter. After 3 seconds, it's gone even further. And so anytime you have a curvy path like this, that means that it's accelerating, because the instantaneous velocity, if we get the slopes, the instantaneous velocity slopes, tangent lines here, the slope keeps getting bigger and bigger and bigger. So the first one, the particle is moving with no acceleration and at a constant velocity, but the second one, the object is moving with an acceleration, and it's parabolic. It's getting faster and faster and faster. So if we take a look at this example, this kind of brings it together. If you look at this cart, this is telling us the motion of the cart and its location every second. So if you notice, after a second it hasn't moved very far, but after the next second it's moved further, after the next second even further, and then really far by the time it's getting to 5. And so even in this 1 second interval, it's moved much greater than it has here. And so that's depicted on here in the position time graph. After 1 second it hasn't moved very far, after 2 seconds it's moved further, 3 seconds it's moved further. So that's why this is curvy. So this is telling us its location, right? But this one is telling us how fast, and really with direction, right, with velocity. So after, it's starting from rest, and then after a second it's going 10 meters per second. After 2 seconds it's going 20 meters per second. After 3 seconds it's going 30 meters per second. So it's getting faster every second. And so with the velocity graph, the velocity time graph, it's increasing velocity at a constant rate. And if we were to get the slope of this line, we would get 10 meters per second squared. So every second, that's how much faster it's getting. The position and time graph here, as we can see, it's exponential. It's getting bigger and bigger and bigger. Now, if we were to compare these three, and we're looking at the motion, the first one is like what we've looked at. The object's moving in the positive direction, and it's getting faster. This one's a little bit different, though. If you notice, if we put time here, like 1 second, 2 seconds, 3 seconds, let's say this was 1 meter location, 2 meter location, 3 meter location. After 1 second, the object's not moved very far at all. After 2 seconds, it's moved further. After 3 seconds, it's really moved further. So in this case, with the second one, the object's moving in the negative direction, and it's actually speeding up. Now in the last one, 1 second, 2 seconds, 3 seconds, let's say, and 1 meter, 2 meters, 3 meters. After 1 second, it's moved all the way from the 3 meter mark to the 2 meter mark, or pretty close to it. Okay, and then after the next second it hasn't moved as much. So in the last one, the object's moving in the negative direction, and it's actually slowing down. So this is a chance to check your understanding and pick the constant velocity graphs. So what I want you to do is you can pause it and then write down which graph or graphs you believe are at a constant velocity, and then you can see how you do. So go ahead and pause it, and then when you're ready you can hit play to continue. Okay, so let's take a look at the first one, position time graph. So this, if we got the slope of this, it's a constant slope, this would definitely be a constant velocity. So this would work. It's a constant slope. Let's take a look at B. What is B telling us? B is telling us our location has not changed. We're still at, let's say this is 1 meter, 2 meters. Our location is still 2 meters. We haven't changed, so our velocity is 0. That works as well. Let's take a look at C. This is telling us our velocity over time. It looks like our velocity is actually decreasing, right? So C does not work because over time velocity is decreasing. And then D, the velocity here is constant. This could be, let's say 1 meters per second. That's how fast we're going. So D works out as well. Now what we're going to do is see if you can draw these from scratch, and this is important to be able to kind of solidify your understanding of the graphs. So for this first one, we want to draw a position time graph, velocity time graph, and acceleration time graph for a stationary object. So go ahead and pause and see if you can draw lines representing the motion for an object that is stationary. Okay, so for an object that would be stationary, we could have an instance here where an object is located somewhere. We could say maybe the object's located at 3 meters and not moving. Therefore, the velocity would be 0. And because they're not moving, and then the acceleration is the change in velocity, that would also be 0. Next, we want to draw an object that is moving at a constant velocity. So let's go ahead and assume for this that this is a person walking to the right, going at a constant velocity, and see if you can draw the arrows representing that motion. So go ahead and pause and try that. Okay, so if the person's moving at a constant velocity, let's say their location was 0 when they started. After a second, maybe they were going 1 meter. After another second, maybe 2 meters. So you're going to have a constant slope with position. And if they're moving at a constant velocity, velocity is staying the same. That's how fast they're going. And then because the velocity stays the same, acceleration therefore would be 0. Now let's try one where we have a non-zero acceleration. Let's make a situation where somebody is walking, but they're getting faster and faster and faster as they go. So go ahead and pause and try to draw the position in time, velocity in time, and acceleration time for someone moving faster and faster in the positive x. Okay, so one of the things that we need to remember with position in time is if we have an acceleration, we know it's going to be curvy. In this case, we'll have a parabolic situation where we're getting faster and faster and faster. The velocity, if they started from rest, is increasing at a constant rate, so getting faster and faster and faster. And if that's true, then the acceleration would be constant because every second they're getting faster and faster and faster.